For those of you that are on Zoom, please type something into the chat so that I can check the attendance. All right. So today I hope to finish up biasing circuits and then move into our amplifier analysis in earnest. So I believe we had just developed the equations for resistive divider biasing when the base current is not negligible. Let me scroll down here. Yes. So what I would like to do now is work an example problem, illustrating the process of determining the operating point of the circuit, and then showing that in this particular example that the current does not meet our specifications for being non-negligible. So let's say that we have the following circuit. .2.5 volt power supply voltage, 5 kilo ohm resistor on our collector terminal, a 170 kilo ohm resistor as R1, and an 80 kilo ohm resistor as R2. So we have increased the resistive divider resistances by a factor of 10 from our previous problem. If we have beta is equal to 100 and IS is equal to 10 to the minus 17, which I believe are the exact same values as before, we want to determine our collector current, IC, our voltage, VBE. We'll also need our voltage, VCE, so that we can make sure it's operating in the forward bias active region. We want to determine if our current IB is less than our current, which I'm going to call IR2, meaning we're trying to make sure that it's negligible. So I'm just labeling things real quick. That we're going to be interested in. And so let's give this a go. So because we are not neglecting our base current, one of the first things that we're going to have to do, if we look at our equations here, is we're going to have to figure out what the Thevenin voltage is and the Thevenin resistance is, right? So Thevenin voltage here and Thevenin resistance goes towards calculating our base current. From our base current, we can calculate our collector current. From our collector current, we can then calculate VBE and VCE. So our Thevenin voltage, V Thevenin in this case, is simply going to be our power supply voltage, 2.5 volts, times 80 kilo ohms divided by 80 plus 170 is 250 kiloohms. And this gives us exactly 0.8 volts. Our Thevenin resistance, I'll put this guy over here, is the 80 kiloohm resistor in parallel with the 70 kiloohm resistor. So that's 80 kiloohms times 170 kiloohms divided by 250 kiloohms gives us a Thevenin resistance of 54.4 kiloohms. From this, our base current is VTH, which is 0.8 volts, minus VT, 26 millivolts, times the natural log of beta 100 IB divided by IS, which is 10 to the negative 17 amps. This whole thing is multiplied by a factor of 1 over R Thevenin, or 1 over 54.4 kiloohms. And so we have, sorry, let me make sure I've got my brackets correct. So we have one equation and one unknown, where our unknown quantity is IB. So using my calculator to solve this, I got 0.624 microamperes. So the first thing I'm going to do is check whether or not I would consider IB to be a negligible quantity here. And so I'm going to compare that to my current IR2, which is VCC over R1 plus R2, 2.5 volts divided by 250 kiloohms is equal to 10 microamps, which is approximately 16 times my base current. Or another way to think about this is that my base current is slightly over 6% of that resistor current, which does not meet the qualifications for neglecting our base current. So from this, we know we're using the right model, although as Mr. Martin asked the other day, would there be any time where it would matter if you used this model versus the other one? And the answer is really no. This one is always a more accurate representation because it's not neglecting the base current. So it should not matter, particularly in your homeworks and things like that, if you always use this model where it's not neglected. All right. So our collector current IC is simply beta times IB is going to be 100 times this, so that's 62.444 microamps. This value gives us VBE is VT natural log IC over IS, which gives us 766.030 millivolts. And lastly, I can sneak it in here, VCE is going to be VCC minus RC IC, and if we put on our numbers there, we would get 2.188 volts. Since VCE is significantly larger than VBE, we are biased well into the forward active region. So before we move along here, is there any questions regarding this example problem or our resistive biasing techniques. Yes, sir. So the current through R2, we are comparing, it's not the actual current through resistor R2. And what I mean by that is we're assuming what it would be if none of the current branched off. And that's how we're making our comparison. So I'm calculating it by dividing simply the power supply voltage divided by the sum of those resistors. But I want to be very clear here that that is not an accurate representation of what the actual current is, right? The actual current through that resistor would be VBE divided by 80 kiloohms. But we're just trying to see, roughly speaking, how this compares to our other model where we neglect the current to see what percentage of that current it would be. So, any other questions on applying this particular biasing scheme? All right, so the principal advantage of this scheme is that it eliminates the dependency on beta that we saw in our simple biasing scheme. That being said, it does have still a reasonably significant drawback, and that is that the collector current is still exponentially related to the base emitter voltage. It has to be. Where that's going to come into an issue is if we look at our diagram here. What if that 80 kiloohm resistor changed by 1%? So it will get increased in value by 1%. What would happen to the base emitter voltage? And let's say that that we can neglect the effects of the base current there, right? So a 1% increase in that resistor R2 would cause roughly a 1% increase in our base emitter voltage VBE. Well, for a 0.01 times VBE divided by VT is going to be equal to, let's say, just for argument's sake, that VBE is somewhere on the order of 0.8 volts, which is a pretty standard number. We've been getting reasonably close to that, plus or minus 50 millivolts this entire. So if we put in 0.8 volts there, the exponential of 0.0, sorry, 0.8 divided by 0.026 is 1.36. So a 1% change in that particular resistor value yields a 36% change in the collector current. So that's a large, large swing there, okay? So what we're going to do to try to fix this drawback is employ what's called emitter degeneration biasing. In emitter degeneration biasing, all we're doing is we're just adding one more resistor, but we're adding it in a very specific location. So here's R1, here's RC. Here's R2, CC. So we're going to put a resistor between the emitter terminal and ground. So this is what a emitter degeneration biasing scheme looks like. This is by far the most commonly used biasing scheme, especially in discrete transistor circuitry. Okay. So let's qualitatively talk about what happens when we include this resistor RE, okay? So it's going to really minimize variations in the base emitter voltage. And so what I mean by that is that resistor RE has a linear current voltage relationship. It has to, it's just a resistor. So if we see some small change in the voltage here, so let's say that we apply some voltage delta V here due to, say, a resistor mismatch or something like that, a portion of that change in voltage is going to occur across the base emitter voltage, so the forward bias of that diode, but a larger portion is going to fall across that resistor RE. And so we can increase the resistor RE, causes a decrease in the change that occurs across the forward bias voltage for that junction, which in turn causes a decrease in the collector current error that we see, or the change in collector current. So to analyze how this thing behaves, it's probably going to be easier, at least for the time being, to use the large signal model. So our large signal model for this guy is going to look something like this. Notice we still have the resistive biasing scheme on the left-hand side. So I'm going to replace that with a Thevenin equivalent voltage in series with a Thevenin equivalent resistance. So there's my Thevenin voltage. Here's my Thevenin resistance, RTH. So this part is simply replacing this bit right here. Then I'm going to have my basic large signal model. Here's my voltage, VDE. Here's my collector. Here's that voltage, resistance RC. Over here is my power supply voltage. Between my emitter and ground, I now have this guy, RE, like so. And this is beta IB, IC, IB, and IE. So if I write a Kirchhoff's voltage law equation around the left-hand loop, what I get, so this is KVL at the left-hand loop, I get VTH is equal to the Thevenin resistance RTH times my base current IB plus VBE, the voltage drop over my base emitter junction, plus RE times IE. Well, I know that IE is simply the sum of the base the base current and the collector current. And so I can express that as simply 1 plus beta IB. So I have RTH IB plus VBE plus RE times 1 plus beta IB. And I'm going to rearrange things slightly. VBE plus RTH plus 1 plus beta RE. And I'm going to substitute in for IB 1 over beta IS EXB VBE over VT. So I have one equation with one unknown VBE, which will then allow me to calculate IC, IB, IE, and all that kind of good stuff. So just to be clear, IC is IS EXP VBE over VT. IB is 1 over beta IC. My emitter current, IE, is IB plus IC. And to check whether or not this thing is operating in the forward active region, VCE is going to be VCC minus RC IC minus RE IE. And I got that equation for VCE by doing Kirchhoff's voltage law around the right-hand loop, where this voltage is VCE. All right. So any questions on how I developed these equations or anything like that? Your textbook specifically neglects the base current, but again, I don't really care for that, so I worked it out without neglecting the base current here. It would arguably make the math a little bit more simple, but again, this is going to be the more correct result. So unless, since somebody has any questions or is willing to say that they do, let's take a peek at an example. So let's say that we have a, what did I call it specifically? Emitter degeneration biasing circuit. 2.5 volts here. 3 kilo ohms resistance. .200 ohm resistor as RE. Here's R1. And we have a 10 kilo ohm resistor in the R2 position. We want to determine R1 if our collector current IC is 0.25 milliamps. So we could argue that we are designing a circuit to give us a specific current One reason we might do that, and this will kind of be the next thing that we talk about. You may remember that the transconductance of a BJT amplifier is IC divided by VT, right? So if we want to design a particular amplifier, we typically design for what that is on the biasing side. That means we are designing for what specific value of IC we want to have as our operating point condition. So we're figuring out what resistors will make that happen here. All right. So we have a fixed collector current of 0.25 milliamps. Let's assume that IS is equal to 6 times 10 to the negative 16 amps. Beta is equal to 100, and VA is equal to infinity. As a second thing, I want to determine what the error in the collector current is if R1 is increased by 5%. And lastly, we could figure out what the collector current error is if R1 is decreased by 5%. So the argument for using this particular scheme for biasing is that we should see a lower error, right? So while 1% variation in a resistor value earlier generated a 36% change in the collector current, let's see if it's smaller. All right. So how are we going to go about determining R1 for a known collector current? Let's, Cameron, what's up? So we could use the large signal model, but we've already developed some equations here, okay? So where in our equations is R1 going to show up? Let's start there. R1 is part of the resistive divider, right? So that means it's going to show up in calculating what V Thevenin is, and it's going to show up in calculating what R Thevenin is. That's the only times it's ever going to show up in any of our equations, right? So with that in mind, we can say that, so we had an equation that said V Thevenin, so that is the same as VCC multiplied by R2 over R1 plus R2 was equal to VBE plus R Thevenin, which is R1 times R2 over R1 plus R2 plus 1 plus beta RE times IB. So we need to figure out what our base current is as well, right? Well, what's IB going to be in this case? Yeah, exactly right. So 1 over beta, or IC over beta, I guess would be a better way to put it. IC over beta. So the only thing in this whole equation we don't know is the value of resistor R1. So if we plug in numbers and solve, we get R1 is equal to 22.743 kilo ohms. You guys can use your calculators to verify that if you want to, all right? So we figured out what exact value gives us a collector current of 25 milliamps. Now let's see what happens if we increase the value of that resistance by 5%, okay? So I'm going to call this R1 prime is 1.05 R1, which would be 23.880 kiloohms. This new value of R1 prime is going to change what V Thevenin is, and it's going to change what R Thevenin is. So V Thevenin prime, which is just VCC times R2 over R1 prime plus R2. When I did the math here, I got 737.883 millivolts. R Thevenin prime, which was R1 prime R2 over R1 prime plus R2, I got to be 7.048 kiloohms. If I plug in these values into my equation, that is, let's see, VTH prime is equal to VBE plus RTH prime plus 1 plus beta RE over 1 over beta IS EXP VBE over VT. Solving this guy for VBE gave me 687.699 millivolts. From this, I'm going to put a prime here just for the hell of it. With this value of VBE, then IC is IS EXP VBE prime over VT. I got 0.184 milliamps. So we see an appreciable change, right? Increasing that resistor value by 5% caused our collector current to drop from 0.25 milliamps to 0.184 milliamps. So the change in IC, which I'll define as follows: IC prime minus IC over IC times 100. We had a change of negative 26.331%. Okay, so that's still an appreciable change in the collector current, right? But we need to remember that that's a change due to a 5% change in the resistor value, as opposed to the 1% change we saw previously, right? So before, an increase by 1% caused an increase of collector current by 36%. Here we're seeing a decrease of 5% gives us a decrease of 26.3% in our collector current. Let's see what happens if we decrease our resistor value by 5%. So that would mean that we would have 0.95 R1, which I get to be 21.605 kiloohms, or 606 would be better. 60585 is what I've written down there. From this, V Thevenin double prime is 790.993 millivolts. using the exact same equations as above. R Thevenin double prime becomes 6.836 kiloohms, which winds up giving me a value of VBE double prime of 702.616 millivolts, which has a corresponding collector current of 0.327 milliamps, and finally a change in collector current of positive 30.754%. Right, they use the exact same equations to generate everything with the double primes as I did the single primes. So we can see that putting a resistor between the emitter and ground here, and this is a reasonably small resistor, right? All of our other resistances are on the order of several kiloohms. Just throwing a simple 200 ohm resistor in there decreased the collector current error by a very significant degree. If we made that resistor larger, we would see that the error would go down as well, but there are limitations to the size of the resistor that we can have because the emitter current that's flowing through that resistor is the sum of the collector and the base, which means we risk driving it outside of forward active region if we make it too big. So that's just something to keep in mind. All right, so any questions regarding this particular problem or the emitter degeneration process? All right. Well, then we have one more biasing scheme to talk about, and it's fairly straightforward. All right. So our last scheme is called self-biasing. Actually, I think we'll talk about it here. So in a self-biased circuit, we have something like this, right? Where here is IB, here is IC, here's VCE, here is VBE. So just by looking at this circuit, you should be able to tell me what the principal advantage of this scheme is. Anybody got any ideas why this is a very useful biasing scheme? So I'll give you guys a hint because nobody's saying much of anything. What's the relationship between VCE and VBE going to be? I would argue that they're not going to be the same. If IB is non-zero, they are going to be different values, right? But VBE, by definition, will always be smaller than VCE. Can't happen any other way, right? So what does that mean? If VCE is always greater than VB, it is impossible to saturate this particular circuit, right? So when VCE is less than VBE is when we enter into the saturation region. So we have VCE greater than VBE for all values of IC, other than, I guess, 0, right? So if we, so it's impossible to put this guy into saturation. So that's a pretty useful scheme, also very, very often used. We can develop our relationships for it pretty easily, right? So we can see that VCC is equal to, oh, sorry, VCE, excuse me, is going to be equal to VCC minus the current flowing through that resistor RC, which is just IB plus IC. So if we do Kirchhoff's current law at the node where the resistors are connected together, we have IB flowing out to the left, IC flowing down. So this current must be IB plus IC. So we will have this is then the same as VCC minus RC times 1 plus 1 over beta times IC. We can also write VCE is VBE plus RB times IB. And since IB is IC over beta, this becomes VBE plus RB over beta IC. And we can set these two expressions equal to each other because they both represent VCE. And in doing so, we get VCC minus RC 1 plus 1 over beta times IC is equal to VBE plus RB over beta times IC. And I'm going to just rearrange things a little bit to, in my opinion, make it prettier. VCC minus VBE is equal to RC times 1 plus 1 over beta plus RB over beta IS EXP VBE over VT. And this gives us our one equation, one unknown, so we can solve for the operating point of this circuit trivially, right? Because once we know, once we use this to calculate VBE, then we can determine IC easily. So let's do just that for a quick example. All right. So if IS is equal to 5 times 10 to the minus 17 amps, and beta is equal to 100, we want to figure out what VBE and IC are. Simple operating point of this circuit. So how are we going to do it? Yeah, I mean, we only have the one equation, so it's pretty straightforward, right? We really just plug in our numbers here. So we know what VCC is, we know what RC is, we know what beta is, we know what RB is, and we know what IS is. So we can solve for VBE using this equation, and we get 807.267 millivolts. And then we can use that to calculate IC using IC is equal to IS times EXP VBE over VT, and we would get 1.525. Nothing real particularly wild there, right? What should we expect to happen if our base resistance is increased? So will VBE, did you say decrease? Yeah, that makes sense, right? If the resistance RB increases, then the base current must decrease, right? That's just good old Ohm's law. If the base current decreases, the collector current decreases, which means VBE also has to be lower. It's just simple relationships like that. So that would be a good theory question I might ask you on an exam, right? Something straightforward like that. All right, we got 25 minutes remaining. So we have two options here. We can get out 25 minutes early, or we can jump into amplifier circuits. You guys' choice. I'm fine either way. No. The homework set for this week is effectively finished up with bias circuits. We would be getting slightly ahead if we did some talking about the common emitter amplifier or something like that. Yeah, let's talk some basics about the common emitter amplifier then. Just because this next section, in my opinion, was probably going to be the hardest part of the class. So maybe having a little bit of extra time would be useful. I need to talk to Dr. Batari about that. If it is, then we might have to pick up the pace a little bit or skip a couple of things.
I may be wrong. I thought initially I saw it.
Let me look at the calendar real quick. How do I look at a calendar? Yeah, the first test was pushed back slightly, but that was to avoid, yeah, like torturing you guys literally the day that you got back. Where's the thing? Well, let me see something real quick here. Louisiana, that is not how you spell. Let's see what's going on. Amplifiers. Okay. So what I'm trying to find is the last day to drop. The last day to drop courses or resign with a W is on Friday, February 5th. So we could move, if we need to, and I'll have to talk to Dr. Batari about this, we could potentially move the exam if it were scheduled for, my best guess would be Friday of next week, which I think would be rude to make you guys take a night test on a Friday night. Yeah. But we could potentially move it to that following Monday, the 1st of February, or the 3rd of February, that Wednesday, and still have time to get everything graded and returned to you prior to the drop date on the 5th. That being said, I am aware I have not yet graded your exam ones. That's on my to-do list. I feel if you guys want to make an informed judgment on whether or not to drop the class, which I don't think you should because it'll put you back a year if you do that. But to make the best informed judgment as possible, I probably do need to get off my butt and grade those tests. So they're currently sitting at my house on my desk. I just haven't done it yet. Okay, so I'll talk to Dr. Batari today about figuring out when exactly that test date is, because again, having a night exam on a Friday is ruthlessly mean. And I don't want to be at work on a Friday night. So unless he's willing to be the only proctor and catch all the flack for it, I'm going to argue to move. All right. So that'll give us sometime today and then 3 days to cover amplifiers. All right. So let's circle back around to this guy. All right. So we're going to talk about the common emitter amplifier. We're going to move reasonably quickly over these first parts to kind of get into the real meat and potatoes of it on Monday, because we've played with this an awful lot. Okay. All right, so as we've talked about previously, the basic topology of a common emitter amplifier looks something like this. We have a resistance RC placed between the power supply and the collector terminal. We ground the emitter terminal. We apply some input voltage at the base and some measure our output voltage at the collector. So by definition, in this base form, we are applying an input signal at the base and sensing the output signal at the collector. Any amplifier which meets these criteria would be considered a common emitter amplifier, okay? Typically speaking, this would be realized with one of these bias circuits that we've talked about before, and we'll talk about how this influences that, but let's start with something real simple, okay? So the 3 parameters that we would be interested in this guy are the voltage gain, the input resistance, and the output resistance, since we're looking at it as an amplifier circuit. So with the early effect ignored, let's look at our small signal model, right? Here's R pi, V pi, GM, V pi. We're ignoring the early effect. Our emitter is ground, body collector. We have a resistance of RC. Goes here. Here's our output voltage. Here's our input voltage. All right, so from this simple circuit right here, we should be able to knock out 2 of our 3 parameters, the input resistance and the voltage gain, okay? So which one do you guys want to knock out first or determine first? Input resistance or voltage gain? Pick one. Input resistance. All right. So input resistance, again, is determined by, we have some applied voltage at the input. We want to know what the ratio of that input voltage divided by the current flowing through that input voltage is. What's it going to be? It'll be Vn over Ix, which is going to be something, right? We can literally figure out what that something is by inspection here. So let's do KVL around this loop. All right, so that would give us Vn is equal to R pi Ix, right? Or negative Vn plus V pi is equal to 0, or negative Vn plus Ix times R pi is equal to 0, however you want to do it. So what's the input resistance? Just R pi. Yep, easy peasy. Vn over Ix is equal to R pi. So this is what the input resistance of our amplifier looks like. Now let's talk about the voltage gain. Voltage gain, by definition, is the output voltage divided by the input voltage. So what's the output voltage here? It's the drop over that resistor RC, right? So what current is flowing through that resistor RC, or what current is flowing through the positive polarity terminal first? Negative GMV pi, all right? So negative GMV pi times RC. That does not look like a V, so let me fix that. Divided by Vn. Well, Vn is the exact same thing as V pi, right? Boom, there's our voltage gain. It's fairly trivial. Our output resistance, I would get by, I'll draw a new small signal model here real quick. Our base, collector, emitter. So between our collector and ground, we are going to have that resistance RC, because we're trying to determine the output resistance. That means we apply our test voltage Vx across our output terminals. So with respect to ground, so here is our current Ix. And what do we do across our base, from base to ground? Because we're measuring output resistance. Talked about this early in class on Wednesday, because today's Friday. Short it out. All right, so what's our output resistance going to be? All right, so let me ask you a question. What's V pi? So we can see that on the top node of R pi, it's connected to the base. and our base is shorted to our emitter. So what's the voltage drop over that resistance R pi? 0, because it's the voltage drop over a short circuit. So if V pi is 0, how much current is flowing or generated by that dependent source? 0. So it looks like an open circuit. So what is our output resistance? Vx over Ix should be what? Well, the only place this current Ix can flow is through that resistor RC. So R out equal to RC. All right, so we know our input resistance, our output resistance, and our voltage gain. So there are a couple of things that we can think about with, okay? One thing that we need to notice is that our small signal voltage gain is negative, okay? So what that means is that if we raise the base voltage, the collector current has to decrease, all right? That's what's giving us a negative gain. The voltage is proportional to the transconductance. So if we want a high voltage gain, we need to bias this guy to where IC is relatively large, right? Because GM is IC divided by VT. So the larger the collector current we have, the higher the voltage gain we have, right? But there's a condition on that, and that is we have to keep our circuit operating in the forward active region. And the larger IC gets, the smaller RC can be to make it still work in the forward active region. The gain also depends on that value of RC. So because of all of these limitations, there is a maximum value for the voltage gain. And I'll sneak that in over here, okay? So the magnitude of AV will always be less than VCC minus VBE over our thermal voltage. All right, that's the maximum possible gain we could ever have. All right. Let's see, there's an example here. Well, we might come back to that one later because I want to address it with the early effect too. All right. So we got 10 minutes left, so let's look at something else real quick. How would this change if we included the early effect? This is where we get into the qualitative analysis of circuits to make this stuff easier, okay? So let's look at our original circuit, all right? If the early effect were included, how would it change our small signal model? We would have a resistor R0 in parallel with that resistor RC, okay? Does that change the input impedance? Not even a little bit, right? Does it change the voltage gain? Absolutely, voltage gain. So with early effect, we know that, let's see, Rn is still R pi, our voltage gain. So if we have that resistor in parallel, that resistor R0 in parallel with RC, our voltage gain equation changes, and we would simply replace RC with RC in parallel with R0. So our voltage gain should be negative GM RC in parallel with R0. How is this going to influence our output resistance? Well, V pi is still 0. We would just have RC and R0 in parallel, and our current would flow through that parallel combination. So our output resistance is simply RC in parallel with R0. So there's an interesting thing going on here. It's only valid for the common emitter amplifier, right? R pi is what? How do we determine R pi? Anybody remember? Figured this out probably a week and a half ago or thereabouts. Beta over GM. All right. So if we recognize that R pi is beta over GM, what our voltage gain for this guy turns out to be is simply negative beta R out over R in. So this lets us, this simple relationship here, lets us figure out how to get a specific gain by choosing values of our input and output impedance. This is another way to help us with design for an amplifier like this, okay? Pretty simple and straightforward relationship there. Works even with the early effect included. All right, so the next thing that we would be talking about is what happens if we degenerate the emitter. So we throw a resistor in there, but that's going to take more than 4 minutes or whatever. So let's stop here. So we've covered some pretty basic stuff. We're going to work an example when we get back on Monday and then jump into, let's see, emitter degeneration, and then kind of screw around with capacitive coupling and things of that nature. Yeah. All right, so I have the web work pulled up, so I just want to look at that real quick to make sure everything's looking groovy. Let's go to the problem list. Problem number 1. This is an NPN transistor, pretty straightforward. Trying to figure out what the, let's see. We know what, we're trying to figure out what IS is such that VCB has a forward bias of 200 millivolts, and then we're trying to figure out what the transconductance is. So we have some bias resistors in place. I think that one should be fairly easy. Next problem. Part A is a resistive divider circuit, pretty straightforward. Part B is also a resistive divider circuit, but we are effectively degenerating it by putting another transistor there. So one thing that you need to think about when looking at part B is that the current flowing into the collector, or I guess a better way to put it would be the current flowing out of the emitter of Q1 has to be the same as the current flowing out of the emitter of Q2 because they're in series. So that's going to aid your analysis significantly, recognizing that. Because if the two emitter currents are the same, that means the collector and the base currents are at least going to be really, really close to each other if they're not exactly the same. The reason I say they may not be exactly the same is because on this guy, there's no resistor. The emitter current is going to split up and then come back together. So just recognize that Q2 is in series with Q1, and that's going to make your life much easier. I think you could probably model it as a simple resistance. Based on that knowledge would be an easier way to approach it. For this guy here, it's similar to the degeneration problem, except that we have a fixed voltage drop over our emitter resistance, really. So we don't really care what it is because we know what the voltage drop is, which should allow us to back calculate things pretty easily. Let's see, problem 3. use an iterative process to calculate the base current of the transistor, do 3 iterations with the starting assumption of VBE is this, so that should be fairly straightforward. Problem 4, we have a self-bias circuit that also has degeneration. So that's going to change our relationships up there slightly, but it shouldn't be particularly difficult because when you do your Kirchhoff's voltage law equations, now you're just going to have to add in R3 times IE into the mix on both sides. And I think that's it. All right, so if you got any questions about the homework or whatever, feel free to email me over the weekend and I'll get back to you as quickly as possible. See you guys on Monday.